Okay, thank you.
Okay.
Thank you.
Thank you. Okay, please start.
Okay. Thanks, Oka, for this nice introduction. So before my presentation, I just like to explain that this work is in collaboration with University of Adelaide and also Flinders Medical Center, who provide us with the data. Yeah, so the talk I'm going to sort of give is just is a recent work that has been published at CHI conference and also a journal in medical imaging. And the talk is called HumanAI Interactive and Continuous Sensemaking through Annotated Attention Heatmaps. So the talk is mainly about how human interacts with AI. So we all know this is a HCI community, and we have done lots of work in the HCI space. And AI, of course, is part of computer application, but when people interact with the AI, it is somewhat different from what we traditionally interact with non-AI computer systems. So my talk, so basically that I will start explaining the problem called two black boxes in human-AI interaction. Then basically that I will explain the ways that we can tackle the two black boxes. One is Explainable AI, that is to unveil the black box from AI to human. Then the other is the human guidance of AI attention, so the human can provide feedback to the AI regarding its own explanation. So that's a two-way of interaction. Then we further move on to explain what is sense-making and how it is different from the traditional interaction. After that, we explain a more streamlined human-AI interactive sense-making. You will know what that means, streamlined, then when we get to that part. So finally, I will use some real-world user cases, particularly from the medical images, the X-ray based medical images, to detect fractures from X-ray images. So I will have a number of examples showing how the technology can be used to improve the prediction performance. So let me just start from explaining how AI is expanding. And we know that AI, maybe 10 years ago or 20 years ago, when people talking about AI, people are quite skeptical about what AI can do. But nowadays, I think people are all convinced that AI is so powerful that it can do lots of things. Some are even better than human beings. For example, in terms of the logic, the classification, performance, that sort of things. Traditionally, the focus of AI has been on algorithmic advances, for example, to design more efficient, more powerful machine learning and deep learning algorithms. Then we move on to the stage that talking about how human working with AI. So we have the AI algorithms, we have the AI systems, how human can work with the AI to do their task. So that is the main thing that is on the rise. And eventually this is more important, probably is more important than the design, the better AI algorithm itself, because it is about the application of AI and how AI can help us perform our task better. So that is basically what is happening. So the scope of AI has been expanded from the traditional model-driven approach to more application-driven and involving human beings in the whole process. So let me start with the traditional human-computer interaction. So we have a human on the one side, we have a computer on the other side. So the computer, when we talk about computer, is basically computer applications. So application running on a computer system. So the interaction will happen in that such a way. So the computer is running application that this application is supposed to help the human to perform a task. So the human knows what the computer can do and what is expected from the human to provide the input. All right, so the human starts with sending input to the computer, and the input is understandable by the computer system. Basically, if you have an interface and the application requires certain input, the human has to provide that type of input. If the input is not right, then the computer or the application will not accept it. So this whatever input provided human, the computer application would be able to understand it. So that is the first stage, the input from the human being, and the input is totally understood by the computer application. After taking the input, then of course the application and computer will, process the input, and some, take less time, some take more time, or depending on how difficult the task is. That will generate the output back to the human. Again, the human will be able to understand its output, because when the human generates the input, so basically we'll know what kind of output the computer application will generate, right? Then the human will process the output and decide whether it has to, this process is over or is not. Then the human needs to generate more input. So the process will go on in such a way that's a kind of human-computer interaction loop. So continues in such a way until the task is complete. So that is a classic human-computer interaction loop. If we replace the computer with AI, and the interaction will be somewhat similar to what traditional human-computer interaction will look like. So again, the human will provide the input data. For example, if the task is an image classification task, so the human will need to provide an image as an input, right? Then the AI will process the image and then do the classification and output the result back to the human, saying this image is what? A dog, a cat, or whatever it is. Then the human needs to process whether the output is right or wrong, if decided whether it will accept this output or not. So this is the kind of process. If the task is not over, more images to be given, then this human AI interaction loop will continue. So the human will give more input, then AI will give more output, then in such a way. So if you look at the human AI interaction loop, is pretty much similar to the traditional human-computer interaction. One thing I did not explain here, because in the previous slide we say, the input is understandable by the computer, and the computer output is understandable by the human. But here I haven't explained that yet. Maybe it's not the case, right? So let's move on to human AI sense making. So how is that different from the human AI interaction? So when we have a human AI interaction, it's all about how human works with AI to complete a task. But whether the whole process makes sense to each other is a different story. So for example, I have a following question to ask in the previous slides about human-computer interaction, human AI interaction. So number one, how does human make sense of AI's output? So in the previous slides, as you can see, the AI will generate an output based on the input given by the human, right? So how does the human make sense of the AI output? If the output says it is a cat, so why it is a cat? Why the human trusts that it's a cat? So that's the first question. The second question is, how does AI know whether its output makes sense to the human? Yes, if the AI is able to explain its output to the human, then how does AI know whether its explanation is making sense to the human? Whether the human does understand what it's trying to explain? That's the second question. If the AI's explanation is not correct, if the human is an expert, all right, clearly that image is not a cat. Then if the output is not correct, so how does the human provide a feedback to the AI saying this is wrong? It's not the right output. So how can the human provide feedback to the AI? That's the third question. If the human is able to provide the feedback to the AI, then the next question is, how does AI make sense of the human feedback? Right? If the human says it's wrong, so how does AI make sense of it? The final question is, how does the human know its feedback makes sense to the AI at all? So the human provides the feedback to AI, and hopefully the AI can understand the feedback. Then how does the human know its feedback has been incorporated by the AI? But suppose the AI will correct its classification from a cat to the right classification. So these 5 questions are all related to the sense making. So basically it's how human and AI make sense to each other in terms of input and output, that sort of things. Okay, so this is the so-called the problem of 2 black boxes. And as we know that particularly the recent AI models, the deep learning models, are all black boxes to humans. So they given an input, they produce an output, but they do not explain the reasoning rationale behind the output. So normally that just user has to trust or not. So that's one black box. So as you can see from here, is from the AI to the human recognition is a black box. The human does not normally understand, or the AI's output does not make sense to the human. All right, the human knows its output, but doesn't understand why it arrives at that output. So that's a different thing. From the human back to the AI is another black box, because the human cognition is also a black box to AI, because the whole system, the whole interaction does not allow the human to provide a feedback to AI's explanation. If AI is trying to explain its reasoning rationale to the human, and how can human provide the feedback back to the AI? So there's no such a mechanism. So these are the black box, the two black boxes. So all the two black boxes are related to the sense making of the mutual sense making between human and AI. And if we only consider the sense making from AI to human, and there's a lot of work already happening, and that's all probably most of us are aware of, that is called explainable AI. So the explainable AI is gaining momentum for human to understand AI's output. So AI, explainable AI is trying to explain its reasoning rationale. So not only just the output or the decision, but also why it arrives at a decision. So that's through the explainable AI. Now, basically, this will open up the black box of AI models to elucidate the reasoning mechanism of a decision to the humans. So the human, in addition to the decision from AI, also it has explanation associated with that decision that will help the user to understand, and the user may choose to trust or not trust the decision. There's some common explainable AI techniques. So, for example, the sharp, the lime, and also EBM, and probably some of you have already used some of the things. They're commonly used in explainable AI, but that's not the focus of this talk. And basically, that the AI making sense of two human is not limited to a certain explainable AI technique. So it's all about the whole principle of sense making. So this slide is borrowed from explainable AI expert, and this basically explains how we position different things in the whole process. So given a task, for example, again, I will always use the image classification as a task, all right? So given a task, you would first need an AI model to perform the task. So from the training data, and you get the AI model, you train the model, right? Then after that is the user will use the model to perform the task. So you have the user here, right? Then this is basically the human AI interaction part, how the user understands the output from the AI, from this AI model. So there are a number of questions. Let me just move this away. Yeah, there are a number of questions that the user might want to ask AI, right? So for example, I understand, yes, you give me this output. I understand why you give me this output. The user may understand. Or the user may understand why you're not giving a different output I'm expecting, right? So I'm expecting a cat, but you're giving a dog. Why? You give me the explanation. The human understands why you succeeded to give the right thing, or you might fail. And these things is the whole process that the human needs to understand why the AI arrives at a certain decision. So explainable AI can be done in two different ways, or a combination of this. One is you come up with an explainable model, right? So the model itself is explainable, and that is not the deep learning. For example, some of the machine learning models like decision tree itself is a kind of explainable model. So you might have explainable model, and the model is able to explain certain features to help the human understand why the AI arrives at a certain decision. Another way is if you don't have the model itself is not explainable, right? For example, deep learning. Then you come up with an explanation interface that's on top of the model itself. So the things we explained in the past, like the sharp or lime or EBM, these are called explainable interface. So it provides a certain interface for the AI model to explain. or you might be a combination of both. So the model itself is explainable. You also come up with a human understandable interface so that the human can better understand the explanation from the AI. So that is basically how the explainable AI is about. So we want to specifically focus on the CNN because the case study we're going to use is image classification. As I have always used that example. So we're talking about the CNN because CNN is a deep learning model itself is a black box, right? And how the CNN can be used to do image classification and how can CNN explain its decision. Of course, you can still apply those traditional or those commonly explainable AI techniques like sharp or lime, that kind of things. But CNN itself is quite special in a way that it comes with a special mechanism. I'm going to explain that later on. So to understand what knowledge is captured by a CNN model, a common way of doing that is you manipulate the input image, then you monitor the change of the prediction result of the output. By doing that, you will discover important classification features. So you change the input, you get a different output. Then you understand what are the important classification features. That's one way to understand what knowledge is captured by CNN. There's another way that is the focus on this talk, is CNN has ability to visualize its attention. So what is attention? So basically CNN will be able to localize the object, the pattern of a particular input that will explain its classification decision. So I will further explain this thing more about this attention. So the technique is called the class activation mapping. And basically that is sort of part of the CNN networks. So it provides object localization maps as a byproduct of the feed-forward inference path. If the network contains a global average pooling layer followed by a softmax classification. So if the CNN has this requirement, so it has a GAP layer followed by a classification layer, then we can have the class activation maps as part of it. And the good thing is that the most of the state-of-the-art CNN models, such as Resident or GoNet, do satisfy this requirement. All right. So that's why with CNN, you can always use the CAM. So there are more recent variations of the CAM which are better than the traditional or the original CAM, and such as called gradient weighted CAM or grade CAM. And that CAM has the ability to actually generalize the localization map beyond the classification networks and with very fine details. I'm going to show an example that you understand the grade CAM is better than original CAM. So this is an example that we use the CAM-based CNN attention visualization to visualize its attention. So there's a number of images. For example, the first image, this is the cat. So how does, this is the original input is a cat. Then you are using CNN to classify that image. And by using the CAM, this is the original CAM. And you can see the features, what the CNN is looking at is the attention is mainly on the forehead of this cat. And this is how it is used to determine the object type. And this is a grade CAM. You can see this has more details. This is a part of the forehead and also some of the legs, I think, that are used to help the classification. And this is called grade CAM plus. This is a better version of that. And you can see the features that are used to make the classification contain the face of the cat, and also the body of it. So that actually basically explains. So when this CNN says this is the cat, then it tries to explain why the CNN determines it's a cat, because the CNN the attention is on this part of, so the face plus the body shape that together decides it is a cat. And other examples you can see are pretty similar. This is another cat, this original CAM. You can see this attention is mainly on the two eyes or something like that, around the cheeks, I think. And this is the grade CAM, we give more details, and this is the grade CAM plus. So the features are, or the attention is mainly on the face. Other things are pretty much similar. This is a dog, and that is also on the face. So this is what is about the CNN attention through we call the CAM-based visualization heat maps. Okay, so we have sort of partially answered the question. That is how AI makes sense of its decision to human through the explainable AI. And it's particular if you're using CNN, and we can use the attention visualization using CAM-based attention visualization. So here's the other half of the problem, all right? So how does AI make sense of humans' feedback? And this is we called the attention guidance. So let me just explain that. So we have answered sort of this part of the question. That is, the AI is able to explain its rationale, decision rationale to the human through visualizing its attention. Then the other half of the human computer sense making is this half. So from human back to the AI. It is how AI makes sense of human feedback. And we call this attention guidance. So the AI is able to explain its attention to the human. And the human can actually guide the AI on its attention. So this is how the whole thing works. So basically that the human guidance of AI attention. So we know that we have the human AI sense making is a kind of a loop between AI and the human. So the the explainable AI is only half of the human AI sense making. And the research on the other half, that is how human can provide feedback to the AI. And the AI making sense of the human feedback is generally lacking. So this part of research, there's not much research in this direction. Most of the research has been focused on explainable AI, which is from the AI to human. From human to AI, this part or this direction is generally lacking. So example here is if the CNN visualize attention, right? And of course, the human can see that. If the human finds the attention is not properly localized, if you say it's a cat, but the features are actually on some of the parts which are not too much relevant to a cat, then the CNN is not paying the right attention. So how does the human provide the feedback to the AI? So the one technique we can do is through the human-computer interaction technique is we can use the human feedback can be overlaid onto the attention, and that is called attention guidance. So the human can guide AI's attention through certain ways or through interaction. So they are the examples of this human guidance of AI attention. So in this example, you can see from left-hand side, is a hand, and it's called fracture detection. So there's a fracture in this hand, in this hand, which is about here, right? But without the human guidance, if you give this image to the AI, to the CNN model, the CNN will say there's no fraction. Why? Because you look at the CAM visualization, the attention is this part. This is using heat map, you can see. So the CNN is paying attention to the fingers, and basically there's no fraction in the fingers. So it says there's no fraction of this image. However, this is wrong. So if I'm a doctor, I'm an expert, by looking at the picture, I know this decision is not right. Why? Because the fracture is actually here, not on the fingers. Therefore, the human can guide the AI, guide its attention, saying, yes, you should look at here, this part, not this part, because what you're looking at is actually not the right part. So by providing this feedback through the scribble interface, so you just scribble here. And then you give the image back to the AI system, and for the AI to retune itself, it can actually localize its attention to the right place. You can see this is the attention that the CNN is looking at. So this is one way of human guiding the AI attention. Another way is a different interface using a bounding box to, again, the similar way that saying that the attention should be on this part, right? So the fracture is likely near this part. And by giving this attention, then the AI will be able to better localize its attention. Okay, so with the two techniques, the Expandable AI, right, using the attention visualization, and also with human guidance of AI attention using attention guidance, then we summarize how human and AI can do interactive sense making. So the process is coming from the human AI interaction to human AI interactive sense making. As we have a human here, we have the AI here. So basically, the first thing is the human will give an image to the AI and ask AI to do classification. So raw image with nothing at all, ask AI to classify this image. So that's first stage. Of course, AI will think, process the image, give output of this image, right? Saying there's no fracture in this image. Why there's no fracture? Because by looking at it, this one, you can see the AI is paying attention to this part, this red part, right? Using heat map, and so the focus is on this part, which has nothing to do with this X-ray. So this is probably a label or something. So nothing to do with this hand. So it gives a classification which is no fracture, and it also explains why there's no fracture, because this is where it is looking at. So this is the second process. All right, the human will process this output by looking at the decision and looking at the explanation and find this has got it wrong because it look at the attention it has paid is wrong. It's not the right area. Then the human will guide AI saying, no, you're not supposed to look at this part. You should pay attention to this part. This is likely the fracture will happen. So the human will provide the feedback back to the AI on top of its explanation. So after receiving this guidance from the human, then the AI will rethink, right? Will rethink itself and then adjust its attention. And in this case, the AI says, yes, I do find a fracture in this image. And then this is why, because this is the part I'm looking at, and there is a fracture here. So this is the whole human AI interactive sense making process. So starting from giving a raw image data, then your AI process, to give a classification result alongside explanation. Human sees the result explanation, and if we find the problem, give feedback back to AI. AI will retune itself. Then, then give a better classification with a more reasonable explanation. So that is the human AI interactive sense making process. So the whole process we captured in this called human AI interaction and continuous sense making framework called Hex Framework, and that framework starts with the AI gets the input, then try to explain its decision through Expandable AI, right, back to the human. So human will sense making of AI's decision through AI explainability, all right? Then the human will be able to understand its explainability and point out whether its understanding is right or wrong, or whether its explanation is right or wrong. So if its explanation is not right, then the human will be able to provide a feedback on top of its explanation. So that's number 2 here. So after receiving the feedback from human, then AI will fine-tune the model using the feedback from the human, right? And fine-tune itself, then do the classification again. So hopefully in this loop, using this framework, then the AI will improve its performance, because by learning from the experts, it knows where it got wrong. Then next time you won't repeat the same error, and the AI will get better in the whole process. So this framework completes the interaction loop for supporting effective human AI mutual sense making. And this the part, as I explained, is alongside the Expandable AI, this side provides the feedback. This side provides the opportunity for human to give feedback to the AI. And the AI has the ability to learn from the human feedback to improve its own performance. And this mutual sense-making loop is especially important to cases where training data is very scarce. And the example I'll use is medical imaging. As you know that getting medical images like X-rays, MRI data labeled by doctors is very difficult. It's very time consuming, and the doctors are all very, very, very busy, and they don't have time for this sort of things. So it's quite difficult to get large number of training data for this kind of applications. So if the training data is not big, is small, then it's likely that the AI model will be overfit to the training data, so it cannot be generalized. So how can we have an accurate AI model with small data? Right, that's the whole question we want to ask. So the thing that if we have this framework in place, then the AI, even is trained by small amount of data, it can still have a good performance because it can learn from the human expert. The human can tell where the AI got it wrong, then AI can learn from the whole process. So even with the small data, the AI can still perform quite reasonably well. So we have also developed an interface for the human to provide feedback to AI. So this is the interface. So this is a raw image, and this is the scribble interface for the human to use. So this is the image here, and the human can say that the attention should be mainly paid on this part using the scribble to tell AI that this is the part that you're looking at, and the part that you have already looked at, which is this finger part, is not right. So you should look at this here, but not here. So this is the interface that is for human to interact with, to provide the feedback to the AI model. So this is the brief AI fine-tuning process. And you can see this is raw, this is the original image, right? And this is the attention visualization from the raw image. And on top of that, the human is able to provide the feedback using scribbles, I can see from this image, right? Then the bottom part is a fine-tuning process. So with the human provided feedback, and they will compare its own attention and find the difference, which is used as loss function. And use the loss function to fine-tune the model. And then hopefully the model will, through the fine-tune process, will get better. Right, so with that in place, I use the real-world case study. It's called fracture diagnosis or fracture detection. And this is particularly using scaffold images. This is from your hand to detect fractures in your hand. You may or may not know that the fracture detection is actually very challenging, representing up to 80% of BIST diagnosis in the emergency department. Because some fracture is so hard to detect, even human eyes cannot detect it. So they have to, use more advanced imaging technology like MRI or CT. However, MRI and CT is more expensive, takes a longer time, and most of the time you still need to rely on X-rays because X-rays is cheap and faster, that kind of things. However, reading the X-ray image requires the doctor to be very experienced. So it requires many years of training and also rich experience to be able to detect fracture from X-ray images. And in some of the case, even the very experienced doctor may not be able to find. So they require further MRI explanation to confirm whether there is a fracture or not. So this is the thing. So with the deep learning techniques like CNN, and it has been used for fracture detection. So there are two issues with using the CNN to assist the doctor do the fracture detection. So one issue, as we just explained, is the data scarcity, because the general training data is very small and the doctor do not have time to label those images. So labeling is a time-intensive and costly process. Therefore, there are not many images available for training. If the CNN model is trained by small data or limited data, that will cause the learning model to overfit only the training data and it cannot be generalized very well. So if you want to, use the model to do classification, it cannot generalize, or it cannot generalize very well. So that's one issue, which is the data scarcity issue. The other issue is the trust. If the doctor wants to use the device from the AI, the doctor has to understand why the AI arrives at the decision, right? So the AI is not able to correctly explain its decision. the doctor cannot trust it. And the two issues can be solved by the Hex framework we just explained, the human AI mutual sense making. So if they're able to mutually make sense of each other, then the trust will be established. And the good thing with that is with the human feedback, and we don't need a lot of training data. So data can be small. The training data doesn't have to be big. So the data set that we used is provided by Flint Medical Center in Adelaide, and basically contains about 1,200 images from 300 patients. And this is the distribution of the images. So we basically that we have a total of 300 patients, and 160 is used for training, and the 40 is used for validation, and 100 is for testing. And then the fracture class and the no fracture is half-half. So basically half fracture and half no fracture. That's what we used for training CNN model. And then this is the result of the classification. And I can see different colors, right? So this this green color is the baseline with no annotation, with no human feedback. This red color is the human provided feedback using bounding box. And this yellow color is the human provided feedback using Scribble interface. So that there are two different ways for the human to provide feedback. And in general, you can see that this lambda here is the weighting parameter. So that controls how much the attention regulation loss is counted into the model. So that from 0.01 up to 5, so the whole process. And in general, if you look at the whole diagram, and especially when the number is between 0.75 and 2, and using human feedback outperforms without using human feedback. So the green is without human feedback, and the red is using bounding box, and the yellow is using Scribble. And next you can see that the Scribble performs better than the bounding box, and the Scribble is significantly better than the baseline. The bounding box is also better, but not statistically significant. So that is the result from the whole thing. It's quite encouraging. So this is the actual example of this classification. So the left-hand side, you can see, if without using the human annotation to give feedback to the AI, and this image, the ground truth is there is a fracture in this image, right? This is the ground truth. Without providing human feedback, and the AI get it wrong. So it says 75% says there's no fracture, and only 25% there's a fracture. So basically, we classify that as no fracture. All right. If the human is able to see the whole thing, why it says there's no fracture? Because if you look at the image here, and the attention it is paying is on the finger part, you can see it's here. So that's why it says there's no fracture. If the human is able to provide the feedback saying you should not look at the fingers, you should look at this part using bounding box, right? Then the prediction performance would be increased significantly. So from 36 no fracture detection to 33% fracture. So which means the AI will determine this image has a fracture. And why? And this is the attention is trying to visualize, which is here, around here, right? There is a fracture around here. So the performance is improved, and it gives the correct decision, and also this is the explanation, right? Similarly, if we use the Scribble interface, right, and that the performance is even better. So it says about 85% confidence that it says, 85% accuracy says it's has fracture, and only 15% says no. And this is actually even better. And this is explanation, the attention visualization, to visualize the attention which is around this location. All right. So this is the good example. let's just revisit this human AI interaction sensemaking. You might ask questions. So let me just try to explain that the whole process again, the human AI interaction sensemaking. So first, the human give a raw data input image, and ask the AI to do the classification. Yes, AI does the classification, will says no fracture and explain this thing. Then you look at this explanation and the result, and just then tells the AI that you have got the attention wrong. You should look at this part, right? The AI will fine-tune itself, then give the correct classification, which is fracture, and also the attention is corrected, focused. So this is the whole process. So the process basically is, first, number one, so let AI do first. So give a raw image without telling what AI should do, just give a raw image and ask AI to do it. Then tell where it should focus if wrong, right? So if the human found the AI has paid the wrong attention, or the region that AI is looking at is not right, then the human will use the feedback, in this case using bounding box, to tell AI where it should look at, right? You should look at here, not the fingers. Then you'll fine-tune the AI, and basically the AI improves the performance. Do you actually need the first step one? Let AI do first, because anyway, the AI may get it right or wrong, and you always ask AI to do the first. If it gets wrong, then tell AI why it is wrong and where you should look at, the correct location you should look at. And you can actually streamline that to make it easier. Is before you ask AI to do it first, you tell where AI should look at. You tell where it should focus, right? Then let AI do. Then in this way, you can remove one more step. There's no need to fine-tune AI itself. So there's no need for trial and error. And if wrong, then tell you why it's wrong, then you try to improve itself. Why not just tell AI in the first place that these are the regions you should look at, then let AI do. So this is more streamlined human AI interaction sensemaking. So it starts from this one. So instead of giving a raw input image to AI and ask AI to process it, so human will first provide the guidance of AI attention. So this, in this case, we're using Scribble or using bounding box. This is just using segmentation. So tell AI, this is the focus region you should look at, right? So then AI will process, because its attention is already guided by the human, right? So it's not human feedback, it's basically human guidance. Then the AI will be able to provide a better localization of the attention, right? So you can see the attention will be localized here. Then the human will process whether the result is right or wrong, whether the attention has been focused on the right region. So that is a streamlined, more streamlined human AI interaction sensemaking. So this is the process that is done, and how AI can learn from humans' attention guidance. So this is a raw image from here, you can see, right? Then the human will use annotation to tell AI the focus region, either using Scribble, using bounding box, or using segmentation, the way the AI should look at. You can see here, this is the image, this is the focus region, and tell the AI you should look at here. So that's this part. And this part is AI to use the cam, as we said, the cam to visualize its own attention. So without knowing its user's guidance, this is what AI will do. Then you will compute the loss, the difference. And the difference will be used to guide AI to focus more on the region that is guided by the human, right? So this is another way of doing that. So by using the streamlined human AI interaction sensemaking framework, then we use Dataset to do the experiment again, and we use more Dataset. So one Dataset is the one we used, we presented in the previous one, which is a scaffold fracture Dataset from Flint Medical Center. We'll also have additional Dataset, which is the ankle fracture Dataset, also from Flint Medical Center, and an external Dataset from a medical center in Netherlands. And this is called ankle fracture. So basically the detection of ankle fracture and it has 3 types of ankle fracture, and as we show in this picture. So 3 locations. So if this part of fracture is called the type A, and if it's here, it's called type B, and if it's here, it's called type C. So the 3 types of ankle fracture. All right, so this data set I can see here. So we have the training set, which is, so basically that we have about the ankle fracture, we have about more than 1,000 images from 578 patients. That's from Flinders Medical Center. Then we have 340 images from this Netherlands Medical Center from 157 patients. So these are the left is the images, right is the patient. So you can see the things from here. The training set, the validation, the test set, and also there's like external test set, the distribution of the data set. So look at the scaffold fracture detection result. And you can see the bars, we have 2 parts, and the lower part is sort of a darker color, and the top part in the lighter color. So the bottom part is called image-wise classification. So it's the accuracy of the image in terms of the image. The upper part it's called the patient-wise. That is how accurate classification in terms of patients, right? If when the number is 1, then in this case, and in most of the cases you can see by using the feedback, either using Scribble or bounding box or segmentation, they all perform much better than the baseline with no annotation, which is the green one, or the blue one. But when the number is 1, we can see all 3 types of annotation, the Scribble, bounding box, and the segmentation, both image-wise and patient-wise are all statistically significant than the baseline. So that's much better than the previous one. Example. This is for input image size of 512 times 512. So if they increase the image size, and then the lambda, if one lambda is 0.1, and most of the cases you can see is statistically significant. So if the number is 1, it's all statistically significant. So this is a better result from previous one. So this is the scaffold fracture example. So in this case, this is a very tricky example in the sense that the fracture is so hard that even the doctor cannot detect it. The fracture is actually here, this green part that's annotated here. So this actually has to rely on an MRI image to decide whether there is a fracture. So this is the fracture is here using MRI. So the human doctor cannot even detect this fracture. All right, so the example here is like, if we don't provide any human guidance, there's no human guidance at all, right? Then the AI is still able to get it right. So decision is right. So it says 99.9%, there is a fracture. Perfect, excellent, all right. However, when you look at its explanation, and you can see here, for example, you see this one. It says that there's fracture, all right? And the heat map actually shows the fracture is around here, which is completely wrong, right? There's no fracture there. So it says the decision is right, but the explanation is completely wrong. Why? It happened to give a correct classification, but what its reasoning is actually, or its reasoning is right, but it has looked at the wrong part. Okay, and if we provide the human guidance, for example, in this case, using the Scribble interface to guide the human attention, right? So this is the attention visualization, and using the 2 different ways of doing the attention visualization. And then they look at this one. So it also says about 99% there's a fracture, and the fracture is about here, or here, you can see here. And which is about right. It's quite close to where actually it is right. It's here. If I'm using segmentation, it's quite similar. It says about 99.5% there is a fracture, and this is why it says there's a fracture. And also similar using bounding box, right? So this is an example that without the human guidance, AI can get the correct classification, but from the reasoning, you understand you can't trust it because the reasoning is completely not right. It's completely irrelevant. So this is the example. This is the result of using the ankle fracture data set, and you can see this is the perfect. So for all cases of the lambda from 0.1 to 1, it's all statistically significant for the ankle data set. And then let's just look at some of the examples. So this is the fracture type C kind of fracture. And this is can see here. So this is the input image. The fracture is here, right? And which is type C fracture. If you're not using human guidance at all, then the AI will say there is a type A fracture. So the 81% says there is a type A fracture. Why? Because it's looking at here. So here, here, or here. Of course, there's no fracture there, right? This shouldn't be the right place. The fracture is actually here. So it gives a wrong classification, and the explanation says it's wrong, confirms it's wrong because it's looking at the wrong region. If you provide the human feedback to AI through Scribble in this case, so this Scribble here says the attention, the attention should be paid along this region. And you can see the AI can get it right. It says about 73% it's a type C fracture, and it's about here, right? So which is quite close to where it should be. If you're using Scribble, if you're using the bounding box interface, it's even higher. It's about 85% say it's a type C, and it's here. If you're using segment, it's even higher. It's about 97% of type C, which the visualize is around here. So no matter what kind of annotation you use, and in this case, segmentation the best, but even the worst one, Scribble, is still get 73% right, 73% accuracy. So which is wonderful. And without the human guidance, the AI gets is completely wrong. So that's one example. There's another example, is a type B example. So the fracture is actually here. It's around this part, and it's actually quite, because of the angle of this picture, it's quite difficult even for human to detect the fracture. All right, so without giving any human guidance in the first place, and the AI will say, all right, there's no fracture. I was 65%, there's no fracture. Why? This is how it visualizes attention. So attention here, no fracture, no fracture. Of course, there's no fracture there, so it says no fracture. If you're using Scribble saying yeah, you should look at this region, right? Then you get it right, about 58%. Not very high, but still get it right. Say it's type B. If you're using the bounding box, right? And you actually get it wrong. It's the same, about 42% say it's no fracture, and it's looking at this part, and the fracture is actually here. So if you're using segmentation, and also it gets wrong, it's about 52% says no fracture, and again it's looking at this part, and which should be here. So this is a very tricky situation, and among the three different kind of annotation styles, only Scribble gets it right, but the bounding box and segmentation, they both got it wrong. This is a final example of no fracture at all. So if this is the image, X-ray image, and this basically is no fracture at all, right? So if not providing any annotation to AI, the AI will get it completely wrong, says it is type A fracture, and it is looking at this part, all right? If you're using the Scribble interface, it says it's type B, and it's looking at here. If you're using bounding box, it says there's no fracture, and it's looking at this part, and found there's no fracture here. And if using segmentation, it's a type B with very high confidence, but it's also looking at this location, there's no fracture at all. So again, it's not always correct, right? And some of the things, the good thing is with three types of annotations, And in the example, the extreme examples we're given here, at least one of them can get it right. Compared to not using any human guidance, which is always wrong in this classification example. Okay, so some closing remarks. As you're all aware that like human-computer interaction, human AI interaction is a very broad area, right? It has many things, you know. The thing that we discussed today is about unveiling the two black boxes for mutual sense making is a fundamental requirement. So to do anything else, to do any other topics, the very foundation is the human must be able to understand AI, and the AI must be able to understand the human's feedback. So this is a very fundamental requirement for any kind of human AI interaction, because without understanding each other, there's nothing else you could do better, right? So on top of that, there are a number of things you can do. Traditional things like HCI, for example, interaction design, how AI and human can actually design, what kind of interaction diagrams, paradigms you can design, UI, UX as well, what type of UX, how human and AI can collaborate, how they can work together to co-create, you know, code, co-create artifacts, that kind of things. Even general things like reliability, the trust of AI, ethics, fairness, and a number of things that in this, the whole human AI interaction space. All right, thank you very much for listening. I'm happy to take questions if you have.
Okay, thank you very much. It's very interesting, and yeah, you have present a lot of with real world example. It's very interesting. I think it's fun. It's the problem of the when we use the pictures of the image, the medical image, especially from the medical. Yeah, I also have joined the group, the research group, and I saw that it's not, because as you said, the doctor is very busy and don't have enough time to to label the pictures. So the limiting images is one of the problems.
Absolutely.
Yeah. Yes. So yeah, very interesting. So I have some question. Have you tried in another area, like not outside the medical education?
Yes, but not as comprehensive as this one. We did try in other type of boat classification, vessel classification, to classify the types of different vessels, but not as comprehensive as this, because we don't have that many vessel images. That's the problem.
Yeah, I understand that, because as I said about the research image for the heart, the heart image, and it's really use a lot of effort to get those data from the hospital.
Indeed. And normally doctors, they are very reluctant to do this kind of job because they are busy enough, they don't have time.
Yes, I truly understand that. I think you have done a lot of work. I think you must have very good connection to the medical center.
Indeed, we really appreciate Flinders Medical Center. So they not only provide us with the images, they also helped with the labeling. So without labeling, there's nothing we can do. So yeah, a lot of efforts in the whole things, because you just can't do it alone as a single group. You need interdisciplinary collaboration in this case.
Yep. And another question is how I wonder how can you retrain the AI to focus only on just a part of that selected part. What is the process that you use to retrain the AI?
So there are two different ways. The very first framework, the very first one is there's a retraining process. It's not retraining the whole model. It's basically fine-tune the AI model. So it's only basically fine-tune the model based on the additional input, the feedback from the human, not to retrain the whole thing, because we don't have new data sets. The second one, the streamlined process, there's no retraining process, because the attention is already, before the AI does anything, the human has already provided the attention to the AI. So the AI, when training the AI model, it already uses the human guidance for the training. So it's not a retraining, it's based the training process. So that's why the second one is actually more efficient than the previous one. This removes the cycle that the AI has to do it first, then when it's got it wrong, then get feedback, then retrain itself.
Okay. Thank you.
But that's a very good question, okay.
Yeah, I will say in Thai ครับมีท่านใดมีคำถามไหมครับ Haifeng, do you have the future plan to do more research, or this is the comprehensive already? I think you just presented.
Along, you mean this work? Yeah, we currently we are not. We did have a plan to continue along this line, but we haven't made a lot of progress. The reason, as you would expect, is quite hard to working with doctors, that kind of things, and it's always they have different agendas. So yeah, we really wish to push this effort, because we haven't done a lot of what should I say is the actual user evaluation of the technology. Yes, we can see the AI performance has been improved, but we actually haven't tested how that will affect the doctor's confidence in taking AI's decision with this technology. This is kind of more traditional HCI type of research. We haven't been able to progress much yet. So yeah, if there's any opportunity we can collaborate, maybe then we can sort of push along this line to more study on the human studies.
Because training here, the model to detect is one issue, but whether the user will accept it or
That's right.
to use it in the future is another story.
Indeed. So are there any questions from the audience? Or
อาจารย์มุกมีคำถามไหมครับอ๋อจริงวัน
Hi, I think there are no more questions from the audience.
Okay, good. Thank you very much. Thank you for the opportunity.
Thank you very much.
Yeah.
See you.
See ya. Bye.
Bye.
Thank you very much.
ขอบคุณมากค่ะ สวัสดีค่ะ